Weak interactions and Neutrino. I have done a terrible thing. I have postulated a particle that cannot be detected. Wolfgang Pauli. One of the most curious and intriguing developments in the really early history of the nuclear and particle physics was the discovery of a brand new force of nature. In this lecture, we are going to be talking about the new force and a very unusual particle called Neutrino that's associated with that force. In the 1930s, people were thinking about fundamental force of nature. A force is a push or pull, as when you tug or push on somebody's hand, or you grab a rope. Those are ordinary, everyday forces. Microscopically, you can ask, if a rope is pulling you, what's really going on is the atoms. Is the atoms in the rope are connecting in some electrical way, electrical way to the atoms in your hand. Yes. But ordinary, everyday forces really boils down to electrical or magnetic in nature. Yes. Then, of course, there is a gravity, which is a fundamental force that we experience every day. By the 1930s, people knew about the strong nuclear force, which is this very short-range force that holds protons and neutrons together, and there was another one that was discovered at this time, and at first it seemed very mysterious. It didn't quite act the same as the other forces. It required a little bit of rethinking about what you mean by force. By the 1930s, people knew about the strong nuclear force, which is this very short-range force that holds protons and neutrons together. And there was another one that was discovered at this time. And at first, it seems very mysterious. It didn't quite act the same as the other forces. It required a little bit rethinking about what you mean by force. Nowadays, instead of using a word force, particle physicists usually talk about interactions. It's kind of the thing. It's kind of the same thing. You talk about, say, an electron and another electron, and they are going to bounce off of one another because they electrically repel. You can think of that as an electrical force, or you can talk about it as an electrical interaction between those particles. If you think really microscopically about that interactions, what's going on? Here is an electron cruising along, and the kind of quantum way of thinking about the force is to say, this electron generates or creates a little photon. Wow, a little photon creates a little photon. A little bounce of the electromagnetic wave which travels across hits the other electron, so it's like tossing a heavy ball between you and me. You toss the ball and you recoil, and then the other person receives the ball and recoils. So that what makes a recoil? The meaning of recoil is that this is a verb. Suddenly spring or flinch back in fear, horror, or disgust. Rebound, or spring back through force of impact or elasticity. The noun, the action of recoiling. Microscopically, I'm thinking about electric force, not anymore in terms of the force between two electrons that are far apart, but in the interaction of the electron and the little photon that it creates. Wow, that's really the electromagnetic interaction in nature. It boils down to an electron which transforms itself into the electron plus a photon. Yes. Or, on the other hand, an electron and photon coming together, which transform themselves into an electron. Wow. That's odd, So there is this transformative aspect of interaction, which is now kind of the integral part of how we think about forces of nature. In the 1930s, people were looking at the radioactive decays. There are various types: alpha, beta, and gamma radiations. One of the type, beta radiation, was very unusual. Well, first of all, beta radiation means that an electron is flying out, but when you look at what's left behind, a transformation occurred. The sort of simplest beta decay that you could imagine is if you take a neutron and it's just sitting there in your laboratory. It sits there for a while and then it radioactively decays. It lasts for a long time and then it spontaneously transforms into a proton and electron and actually something else, a neutrino. Yes, neutrino. But that was not visible in the 1930s, so as far as the experimentalists were concerned, the neutron simply turned into the proton plus an electron. So what caused that to happen? We now use the phrase, the weak force. Yes, the weak force. It was a weak interaction of nature. It was not electromagnetic. It was not some strong nuclear force. It was a transformation. Weak force is a transformation. It was a transformation. So this is a sort of a novel way of thinking about the force. That's not really a push or pull. Wow, new concept, right? Yes. It's a force of nature that causes radioactive decays. Aha. So weak force causes radioactive decays. Yes. Now, since then, the weak force has also been demonstrated to cause pushes and pulls. Neutrinos get pushed and pulled by the weak force, but the origin of this force was more transformative than it was pushing and pulling. When you have a force of nature, now we are thinking about it is involving a force carrier. So electromagnetism involves a photon, which is the particle. That's transfer that causes that force. Mr. Yukawa, in the early 1930s, mid 1930s, proposed that the strong nuclear force that binds proton and neutron should be thought of as involving the exchange of the pion, a pi meson. So again, it's a little particle that's transferred. The pion was really a particle, an honest particle. It had mass and it could have an electric charge. In the later years, you could find a little track of these pions in the bubble chambers because you could actually create one of those things. What about weak force? This is a new force of nature. What kind of a force carrier does it have? Now, this idea really didn't develop in the 1930s. The idea of force carrier for the weak force was developed more in the 1960s and even later, where it was refined. We now call it the W for the weak. So it's a W particle. Wow, I've never heard this terminology before. Actually, there are two W particles because they can be electrically charged. You can have a W positive or W negative. We call it the W plus and the W minus. Wow. W have a third one now, Z, because it's got zero charge. Yes, so there are really three possible forces carriers. Wow. So there are really three possible force carriers. We call it the weak interactions. And why is it weak? If a neutron decays and proton and electron go flying out, that doesn't really look all that weak. They've got lots of energy and they leave good tracks. It's really easy to detect and measure. It seems like a fairly dramatic decay. The reason we call it weak is because it's very improbable. Wow. A neutron lives for a long time, so it's not so much that when it happens, it's wimpy. It's that it's just unlikely to happen. Why is it unlikely to happen? Because the new force carrier, the W, sometimes called the double boson. Double boson. And we will learn what bosons means later. This W particle is extremely massive. Remember when I was talking about the strong force? I said, here is a proton and here is another proton. Why do they stick together? Because one of them creates a pi meson, and the pi meson is massive. Now you are actually asking nature to create a particle out of nothing, and that seems like it violates conservation of energy, which is a pretty crazy idea. Yes. You can only get away with this because of the quantum mechanics. Quantum mechanics says, yeah, you can create energy out of nothing, but just for really short time. So the pi meson can live for a really short time. It has to be eaten up by another proton or neutron right away. And the more massive the particle is, the shorter of the time you are allowed to borrow it from nature. That's the Heisenberg uncertainty principle. So the W particle is so incredibly massive that the amount of time that you can borrow it from the nowhere is extraordinarily short, and that's the origin of the improbability of the weak force. The weak interactions. You are just asking nature to give you the huge bundle of energy. The mass of the W boson is something like 80 times more than the mass of a proton. Whoa! So it's huge. In general, in nature, when weak interactions are present, they are very improbable. So it's kind of like the lottery. It's like a kind of lottery. The odds for any individual to win are very low, but when it happens, it can be quite dramatic, and the evidence is very clear once somebody wins the lottery. Yes, it is obvious because he's gonna be extravagant, right? Why do we care about the weak force? You've never felt it. You know, this pull, it's not weak. Even when it is weak, it's not the weak force. It's not a part of our everyday life. Neither is the strong force, but the strong force is incredibly important. The strong force is responsible for nuclear energy and nuclear weapons and the solar energy, right? That's what's powering the sun. The weak force is a little more obscure, right? As we go on in this course, we'll be finding more and more obscure particles and interactions that somehow seem less connected with our life. The weak force does play some roles. For example, beta decays, radioactive decays are quite common. Lots of radioactive materials decays this way, and typically weak decays mean long lifetime. So, for instance, in the medical technologies, if you want to image the inside of somebody, you might inject them with some radioactive material, and typically you'll use the material with a long lifetime. Yes. You want something that might beta decay so that it doesn't just radiate away right away. You need some time in order to make some images. It has some practical applications in medicine. Some street signs, not street signs, but lighted signs in the buildings. Have tritium in them, which beta decays. It lives for a long time and grows a little bit, and actually you can make the decaying beta particles make some red signs light up and say exit. There is actually a much more important role for the weak interactions that is critical to our lives. Inside the sun, the main power generation is a strong force, a proton from hydrogen and another proton from hydrogen. It's very, very hot, slammed together. they stick by the strong force, and that sticking actually ends up releasing some energy, which is a power supply for the sun. The problem with that is that the proton and the proton sticking together would form something like two protons, and that's not a stable nucleus. So they would actually just come together and fly back apart again, and the sun wouldn't work if there are only the strong force. So what do you need? You need the proton and neutron to come together. Proton and proton to come together, and then one of the protons has to transform into the neutrons. Okay? Into the neutrons, because the proton-neutron system is stable. Proton-neutron system is stable. That's perfectly content nucleus. You need both the strong interaction to release the energy that's a supplier of energy, but the weak interaction absolutely critical. You need the transformation in order to stabilize the final product, so the weak interaction plays this critical role in making the sun work. Wow! Didn't know that? Even more important than that, you might argue, is that if you wanted to build up more complicated nuclei, if you want to take two of those things and slam them together, and then two of those things and slam them together, which is what happened in the stars, especially towards the end of their lifetime, that's the way you build larger and larger nuclei. Alright? That's how you build the carbon and nitrogen and oxygen. I don't know if you ever thought about this, but your body is filled with atoms that have nuclei, carbon and nitrogen and oxygen and so on, that are all very big. Where did they come from? I mean, where did you come from? You started off little and you've grown this big. Where did all those carbon atoms come from? Now, you might say, I ate them. But where did food carbon atoms come from? Well, you might say they come from planet Earth, but where did the planet Earth come from? Ultimately, all of that stuff, all of the heavy atoms, everything beyond the hydrogen that we are made of, must have come from some nuclear process in the star. In a star, yes! Must have come from some nuclear processes in the star, not our star, because our star hasn't gone supernova yet. Wow! So it must have been actually a previous generation of the star which underwent this nucleosynthesis. Nucleosynthesis! Wow! Is it called nucleosynthesis? Wow! And build up the larger nuclei, for which the weak interaction was absolutely critical to do a transformation from one nucleus to another. Let me repeat this sentence because this is so sweet. Okay? So, I don't know if you ever thought about this, but your body is filled with atoms that have nuclei, carbon and nitrogen and oxygen and so on, that are all very big. Where did they come from? I mean, where did you come from? You started off the little and you've grown this big. Where did all those carbon atoms come from? Now you might say, I ate them. But where did the food carbon atoms come from? Well, you might say they came from the planet Earth, but where did the planet Earth come from? Ultimately, all of the stuff, all of the heavy atoms, everything beyond hydrogen that we are made of, must have come from some nuclear process in the star, not our star, because our star hasn't gone supernova yet. So it must have been actually a previous generation of the star which underwent this new nucleosynthesis and build up a larger nuclei for which the weak interactions was absolutely critical to do the transformation from one nucleus to another. So the weak force is in some sense responsible for all of the stuff we are made of. So cool.